So here we want to look at the ideas of what the graph of the derivative tells us about its function. And these questions can get deceivingly tricky because you're used to probably looking at things the other way around. But in general, I'll just start with this, that if we have a function, you see in blue here, this is some function f. When the function is decreasing, it's going down, its derivative we know will be negative. And so the same thing over here. This function over here is going down, so whatever the derivative is in that interval, it's got to be negative. It's not going to be a constant negative. Sometimes it's going down at a faster rate than others, but it will be negative. And the other way around, if a function is increasing, its derivative must be positive. Finally, if the function is not increasing or decreasing, if we have a turning point at those instants, the derivative must be 0. We've seen these ideas before. What's going to make it more challenging is looking at it the other way around, where, like in this question, this graph here is not f of x, this is the derivative. So I'm just going to label this just to be clear. This is not f of x, this is the derivative. But from this, we want to try to understand some characteristics of f from the derivative. So we're looking at the other way around. And so what says here, what must be greater, f at 0 or f at 1? So if I look at my graph, when x is 0, this derivative is at 0. When x is 1, this derivative, that's at 2. The derivative is down here. But again, I'm not asking what's greater for on this graph when x is 0 and x is 1. This is the graph of the derivative. I'm asking about the actual function, f, not f prime. And so in this case, if I look here, if I look at when x is 0, my derivative is exactly 0, which means at that instant, this graph is not increasing or decreasing. After that, my graph goes down, and because the derivative is negative. And at this point here, the graph has been decreasing for a while. So whatever the function was when x was 0, I know it's been decreasing by the time we get here. And so I don't know what these values are, but I do know the function has gone down between 0 and 1, which means I know f at 0 must be greater. It's impossible for me to know what f at 0 is because I haven't been given enough information, but I know it must be a greater number than f at 1. And so now looking over here, f at 1 and f at 2. So here's f prime at 1, here's f prime at 2. And again, we got to be careful because it's easy to look at these and go, okay, well, when x is 2, this point here that I'm kind of showing extra big dot in red, it's higher up, so it must be a greater value. And that's true for the derivative. The derivative is greater at that point, but for the actual function, that's not true because at this point, whatever the function was when x is 1, even though my derivative is going up, it's still a negative value, which means from here to here, my function is still going down. So whatever this value is when x is 1 on my function, it is still going down. The derivative is getting closer to 0, which means it's not going down as quickly, but it is still going down. And so I know by the time we get here, it must be lower because the derivative the entire time between these 2 points has been negative, which means the entire time the function has been going down, it's been decreasing, which means whatever this value is when f is 2 must be less than when f is 1. So f is 1 must be greater. And I'll do a bit more to visualize this in a moment, but let me answer one more question here. How do the x-intercepts of the derivative relate to the function? I've already kind of mentioned that earlier on. The x-intercepts are, in this case, 0 and 2. That's where my derivative is 0. That's where this function is not increasing or decreasing. These are the turning points. And so in this case, the x-intercepts of the derivative are turning points. Now, while I'm done this question, like I said, these questions can be deceivingly challenging. And if you're not finding it challenging, fair enough, and don't get overconfident. But it is easy to confuse ourselves. And so to make this a little more concrete, I'm just going to show, what you see already. This is the graph of the derivative. But here's an example of what the actual function f looked like. Now, if you look at the equation here, x cubed minus 3x squared, that's the key part. I have this little plus c, and right now that c is 0. I'll talk about that in a bit. But here's one example of what the actual function f looked like. There's other examples, which I'll get to. But this is probably the simplest. And so if you look at this compared to the derivative, notice there are 2 turning points at 0 and 2. But notice as well that from this region between 0 and 2, it's going down, but then it starts to go back up after that. But this whole region between 0 and 2, it was going down the entire time, which we can see from our derivative. Between 0 and 2 on the x and the derivative, my derivative was always negative. Although I will say this is just one of an infinitely many possible functions for f that would have this derivative. So if I take my slider here, because I c is a constant, it doesn't actually matter what that is. If I make c a positive number or a negative number, it does change what f of x looks like, but notice the derivative is not changing. Because as we'll learn later on, whether this function has looks like this or whether it looks like this, how it's changing, how the slope is changing is the same between all of those. That's it. Hopefully that makes it a bit more concrete, but again, all of this, I said from the start, can be deceivingly challenging, especially when you don't have that and you're looking at the derivative and you want to go the other way around. All right, so here again is a graph of a derivative. And I'm just gonna, if I look at this, if I look at my y-axis, it's not even labeled what these values are, but my x-axis is clearly labeled. So for what interval or intervals is f of x increasing? Which means, since this is the derivative, this should be fairly quick. Anywhere my derivative is above the x-axis, anywhere my derivative is positive, my function is increasing. And so for this, my function is increasing anywhere less than 1, not equal to 1, when x is less than 1, and where x is greater than 4. I can't say if I put less than or equal to or greater than or equal to, that is going to be incorrect, because when x equals 1 or equals 4, it's not increasing or decreasing. That's the instant it's a turning point, it's changing direction. And so that's where it's increasing. Where is it decreasing? Well, this interval from 1 to 4. That's the only interval in which my derivative is negative, and so between 1 and 4, using whatever notation you want. Okay, how must the values of f at 2 and f at 3 compare? Not f prime at 2, f prime at 3, f at 2 and f at 3. So if I look here, f at 2, well, if I look at my function, the derivative at 2 is some negative number right here. F at 3, if I look at my derivative, the derivative at 3 is some value there. It looks to be the same. This seems to be a symmetrical quadratic function. But again, I'm not asking about how the values of the derivative compare. How do the values of f at 2 and f at 3 compare? And so the key is, between these two values, my function is still decreasing the entire time. It was decreasing from here to here. From 1 to 2, it starts decreasing. It keeps decreasing. It keeps decreasing by the time we get to 3. And in fact, it keeps decreasing all the time we get to 4. That's what we answered before. So that means if I compare just these two, whatever my function was when x is 2, it has decreased more. And so f at 3 must be a smaller number. It must be a smaller number compared to when f was at 2. And so I know that f at 2 must be greater than f at 3. Or f at 3 must be less than f at 2. So now in the interval from -1 to 4, where must f of x be greatest? And so let's erase all my scribblings and look at this interval from -1 to 4. So looking from here to here, where must f be greatest? And again, we got to be careful. It's pretty easy to look at this point right here and go, well, that's the highest point. And that's where the derivative is greatest. But where is the function greatest? And so let's think about what's happening here. In this region here, my function is increasing. It's not increasing at a constant rate. In fact, the closer it gets to 1, the more it kind of levels out, but it is increasing. So whatever my function is, whatever value it is when x is -1, I don't know, but I know it keeps going up. It's going up, it's going up, it's going up. Right here, it turns and starts going down. So it's going down, it's going down, it's going down, it's going down. Then right here, it has another turning point, but that's where we stop looking. So keep in mind, this function was going up the whole time here, then it started going down, which means right in between there, that must be the highest point. And so when x equals 1, that must be the highest point of this function in that interval. Oh, I made a mess of that. And so now, let's get an idea of what a possible sketch could look like for the function. I showed you just in the previous one on Desmos. And so in here, what I would do first is realize, okay, right here, I already know that's the highest point. That's from the last question. How high is it? I don't even know. It may not even be above the x-axis, but I'm going to draw something, I don't know, right here. Okay? To the left of that point, it is increasing the entire time, but as we get closer to 1, it's increasing less and less and less, which means it must look something like this, where it's going up, but as we get closer to 1, it kind of levels out and for an instant flattens out. We know from before that it's decreasing from here to here. And so this next little interval, it must be going down. How down, I don't really know. I'll just kind of draw something like this. But by the time we get to 4, it must sort of level out again. Because remember, 4 is a turning point. At 4, it's not increasing or decreasing. And then at that point, it just starts going up again. And so I have it going like this, and there we go. Here's one possible sketch. Keep in mind, everything I've drawn relates back to what I've mentioned. Between 1 and 4, the function is decreasing. When it's less than 1 or greater than 4, the function is increasing. Remember, we always look at a graph from left to right. And the highest point of this function must be when x equals 1. So like I've said before, if you do not find any of that challenging, be humble about it. Don't get overconfident, but usually students at first find this quite challenging, actually. All right, lastly, I got, again, a function, but it's the derivative. So it's g prime of x. I want to know where g is at its minimum. And so for this, what would help a lot is to graph this. Pretty easy to graph in any GDC. So let me go to Desmos here. And here is the graph of 2x cubed minus 5x squared. Keep in mind, this is the derivative. And so I want to first know, where's this function at its minimum? And so looking here, let's see what's happening here. If I look at my graph, kind of pick a point on it. All along here, this is my derivative. And so what matters here is my derivative is negative. And so whatever my function looks like, it is decreasing. It's going down, 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 down. At this instant, it's not going down very much. At this instant right here, it's leveled off, but then it starts going down again. So it's still, this whole region here, my function is decreasing. Right here, it's still decreasing because I'm below the x-axis, still decreasing. And it's not till I get right here that not only does it level out again, but it actually for the first time starts to increase, which means everything from here, which goes forever down, all the way to here, it's never going up. And so, which means this point right here, when x is 2.5, that must be the lowest point of the function. It has to be, because everything to the left of it, my derivative has been negative. Or at one point it was 0, but then it kept going down again. And so this point here, when x equals 2.5, that must be the lowest point of the function, because after that, it just keeps going up forever. And so the lowest point of the function must be when x equals 2.5, or 5 halves. It's the only minimum. So when's it at its maximum? Well, if I go back here, remember if I look at my graph, I can see it doesn't have any other turning points. And remember, this is the derivative. So I said for all along here, everything, this whole region going all the way down, my function is decreasing. And it's, which means my function, if I imagine the graph, it's coming from the top and infinitely high and coming down. It's going down, 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 down. And then at this point, it starts going up. And only in this region here is it actually going up, and it goes up forever. So what must this look like? Well, that means my graph must look something like this, where it's coming down, it does some stuff, okay? But then it starts going back up forever, right? It's going down, it's going up, which means there must not be a set number where x is at its maximum. My function must go up forever over here, and it must go up forever over here, which means this function doesn't have a maximum. So I could say there is no maximum, but we've learned a little bit limits, so I'll say this instead. I'll say as x approaches negative infinity and as x approaches positive infinity, that's when this function has its maximum. Or we can say the limit as x approaches, I'll put plus or minus infinity, of g of x, it will equal infinity. So while it doesn't have a maximum, does keep going up forever. And so since I've mentioned some things about limits before, that's the first lesson I thought I'd mention here. And lastly, I'll show you what, again, one possibility is. What you see here in purple, this is one possibility for what g of x could look like. I'll turn off the derivative for a second. And notice it just keeps going up and up forever. I don't need to zoom out. Notice when x was 0, it was a different type of turning point. We call this an inflection point, but it then just kept going down. So notice it really was at its lowest point at 2.5, and then it starts going up for the rest of it. All right, so before I stop, just for all these, be careful. It's probably one of the first times you have to think about a function from looking at how its rate of change. And it's most likely a new idea, which makes sense that it's challenging.